Hello everyone, this is Dr. T. Bhargava Ramu, Assistant Professor, EEE, MLR Institute of Technology. We were discussing regarding underground cables. In previous class, we discussed about classification of cables and parameters related to the underground cables, that is resistance parameter and capacitance parameter and conductance parameter. So these three parameters we discussed, and dielectric strength parameter also we discussed in previous class. So in previous class we discussed regarding capacitance parameters like resistance, capacitance and dielectric strength of the underground cable. So in today's class we will discuss regarding grading of cables. So why grading of cables are needed, and next capacitance grading is one kind and intersheath grading is one more kind, and conclusion part of the today's class. So we will discuss in our class today grading of the cables, that is capacitance grading, intersheath grading and conclusion part of the gradings. So first, so what is grading of cable? So as we discussed in previous class, suppose if we have any underground cable cross section, if we consider like this, so within this underground cable, if you see the dielectric strength of the cable, that dielectric strength will vary from center of the conductor to the edge of the underground cable. So the dielectric strength value will be vary from center point of the underground cable to edge point of the underground cable. So due to this in ununiform of dielectric strength, so unnecessarily expenditure will be more on making the underground cables. So to overcome the above disadvantage, it is necessary to have uniform stress distribution. Uniform stress distribution is needed in underground cable. So to avoid this unnecessarily expenditure on the underground cable, we need uniform stress distribution in the cable is needed. The process of achieving uniformity, electrostatic stress, that is dielectric strength in the underground cable is called as grading of cables. So what is the meaning of grading of cable? The grading of cable is needed to make the uniform stress in the underground cable. Grading of the cables is needed. So the process of grading of the cables is called as, the process of achieving uniform electrostatic stress in the cables is called as grading of the cables. So we have generally two kinds of grading phenomena are there, that is capacitance grading is one kind and intersheath grading is one more kind. Capacitance grading is one kind and intersheath grading is one more kind. So we will see one by one. So first, capacitance grading. So as we discussed, so if you see in this figure, it is given that number of concentric circles within the underground cable, different insulating materials are placed at different radius or diameters. Okay, the process of achieving uniformity in the dielectric stress by using layers of different dielectrics. So this is very important word, layers of different dielectrics. That means if you take any cable, so as a layer 1, outer layer, one kind of dielectric material we will use, and in another layer one more dielectric we will use, and another layer one more dielectric we will use. Like that, different layers of dielectric materials we will use to achieve the uniformity of dielectric stress. Why dielectric stress uniformity is needed means, so there will be voltage difference between layer to layer. So due to this, insulation cost will be more. To reduce the expensive in the making of underground cables, so we need equal dielectric strength from center to the outer edge of the underground cable. So that kind of making of uniformity is called as capacitance grading. That means, so different dielectric materials we will use, as layers by layers, so that we will get uniformity dielectric stress in the underground cable. Next, the homogeneous dielectric is replaced by composite dielectrics. That means it is a composition of different dielectrics. The homogeneous dielectric means instead of taking single dielectric, we will use that means homogeneous dielectric means single dielectric. So instead of that, we will replace that single dielectric with composite dielectrics. That means different layers of dielectric materials we will use. The composite dielectric consists of various layers of different dielectrics in such a manner that relative permittivity of any layer is inversely proportional to the distance from the center. That means, suppose if you take outermost dielectric layer, this layer we are considering. If we consider this outermost dielectric layer, so the distance is more. So this distance is inversely proportional to the permittivity of the dielectric material. Like that. Suppose if you take one more layer, this is small d, capital D. So inner layer is distance is different and outer layer distance is different from the center. So the distance is inversely proportional to the permittivity of the dielectric material chosen. Like that we have to consider. That means in that manner if we consider, then automatically the uniformity will come. The layers and layers, if you take with inversely proportional permittivity model, the uniformity of dielectric stress will come. Suppose from the center, distance from the center as we discussed. So if we consider this is maximum dielectric stress of a with distance r and maximum dielectric stress with some other material of at r1 distance, and this is r3 distance. This is max 3, it is G max 3. That means as we seen here, so there is it's a conductor radius is r, at the conductor radius is r, at the, suppose if this is the conductor, at the conductor edge point, the maximum stress is given by q by 2 pi epsilon 1 r, it is q by 2 pi epsilon naught r, this formula represents. Suppose if you take a layer outer side of this one layer with radius r1, as shown in the figure, this r1 from center to here. So that is given by G max 2 q by 2 pi epsilon to r1. Similarly, G by 2 pi epsilon r3, like this. So different layers, electrostatic stress, dielectric stress value is given with these three formulae. To have same maximum working stress, so these three values should be equal. In order to get equal stress, these three values should be equal. From this we can write epsilon 1 r equal to epsilon 2 r. This relation we will get finally. If you observe this relation, it shows that the permittivity is inversely proportional to the distance from the center. Still, if we consider, if there are three dielectrics outer diameters, let it be d1, d2 and capital D. Here it is represented with a diameter, we can make it as a radius also. Relative permittivity of the dielectrics, first dielectric is 1 and second one is 2 and 3 are such that, so dielectric permittivity value is more. That means, so here you see epsilon 1 value is more, epsilon 2 value is more, epsilon 3 value is, this is, again I am redrawing the diagram which is represented there. So this is epsilon 1, this is epsilon 2, this is epsilon 3. So this epsilon 1 dielectric material distance is, otherwise radius is, let it be some r1, and second one is r2 and third one is R3. So the dielectric material's distance from the center is R1, R2, R3, and the permittivity of the dielectrics is epsilon 1, epsilon 2, epsilon 3. So in which fashion we have to take to make the uniformity of dielectric stress means, so this relations those should satisfy. Then we will get equivalent dielectric stress within the underground cable, right? Next, similarly, so three dielectrics are worked at the same maximum stress. You see, at any edge of the conductor, at any edge of the dielectric material, the maximum stress will occur. So these maximum stress value should be equal. So that is given by epsilon 1 d, epsilon 2 d1, epsilon 2 d2. So similarly, with this, the potential difference between center and to the edge of the dielectric material is given by V1, V2 and V3. These are the formulas. Potential difference between center of the underground cable to the edge of the dielectric material. So total potential difference between core and sheath. Core and sheath means the center part is called as core, this is core, and this is outer sheath. So total potential difference between these two is given as V1 plus V2 plus V3, whereas V1 is up to this point voltage, and up to this point voltage difference, and up to this point voltage difference. So those three values, if you add up, we will get total potential difference between conductor and the outer sheath. So by distributing this stress uniformly, the breakdown of installation can be avoided. So if you are not maintaining the uniformity stress within the underground cable, breakdown may happen. So to avoid these breakdowns, insulation cost will be more. To avoid these insulation cost more expensive, so we can have a grading of the cables. Next, coming to the next model of grading. Next model of underground cable uniformity of dielectric stress grading is internal sheath grading. We can call it as intersheath grading also. Internal sheath grading or intersheath grading. So in this, homogeneous dielectric is used. In previous case, that homogeneous dielectric is replaced with different types of dielectric materials. Different types of composite dielectric materials we have used. So here homogeneous dielectrics is used. Dielectric is divided into various layers by placing metallic intersheaths between the core and lead sheath. The difference between capacitance grading and internal sheath grading is, we will use same material as dielectric material from center to the outer surface of the cable, but these dielectrics are separated with metallic sheaths, metallic intersheaths. So some metallic intersheath is placed in between this place, and some more metallic intersheath is placed at this place. So this is the intersheath grading. It is internally we are creating sheaths, involving sheaths between the dielectric material within the same material. The intersheaths are held at suitable potentials which are in between the core potential and earth potential. That means, so different places are chosen at different radiuses, that metallic sheaths are introduced. So this arrangement improves voltage distribution in the electric of the cable, and consequently more uniform potential gradient is obtained. So by making this intersheath grading, so we can have uniform potential gradient within the conductor, within the underground cable. See here. So this is lead sheath, outer sheath is lead sheath. So internally after the core, so intersheath 1 is included, and in between intersheath 2 is included. These two are the two sheaths, and this is lead sheath is outer sheath. So if we consider D is the diameter of the cable core, center core diameter is D, capital D is outer diameter of the lead sheath, two intersheaths of diameter D1 and D2 are at D1, D2 diameters, the two intersheaths are fixed within the material. Then V1 is the voltage between conductor and the sheath. That means from here to here voltage is considered as V. Similarly, V1 is the voltage between conductor and intersheath, sheath 1 and conductor. This part is V1 and next part is V2. V1, V2 and V are the different voltages between the sheaths and conductor. So every cable will have a lead sheath at outer side. So to make uniform stress within the cable, we inserted two more sheaths. We involved in two more sheaths within the cable, that is sheath 1 and that is sheath 2. So V1, V2, V are different voltages between the sheath and conductors. As there is definite potential difference between the inner sheath and outer layers, and each sheath can be treated like homogeneous single core cable. This is the conductor core and one sheath is there. We can consider this as a single core cable. We can consider this as a single core cable. So by considering like that, so we can have G max at this edge of this dielectric material or sheath. Let it be sheath 1, internal sheath. So that G max value is given by this formula. Similarly, if you consider one more sheath, that is sheath 2, which is at a distance D2, which is with a diameter of D2. So again G max value for this, by considering it as one more single core cable, so the value is given as G2 max. This is G1 max, this is G2 max. Similarly, lead sheath is there, one more outer, again you consider that as, they call it as G3 max. So these three formulas will give maximum potential gradients, maximum dielectric stress at the surface of the sheaths, So next, to make equal distribution, so these G value should be equal, must be equal to make uniformity of stress within the cable. So if we equate all these formulas, we will get like this. As the cable behaves like three capacitors in series, there are all the potentials in the phase voltage between the conductors are enhanced. Lead sheath is V1 equal V2 equal to. As we discussed previously, the total voltage between conductor and outer surface is given as V. So that total value will be given by V1 plus V2 plus V3. Like this, we can achieve the uniformity stress within the cable. So if we conclude, there are some disadvantages also related to intersheath grading. There are complications in fixing the sheath potentials. So we are considering it as sheath potential V1, V2 and V3, like that we are considering. To fix these values, there will be some complexity in the making V1, V2, V3 values, perfect values. And another disadvantage is intersheaths are likely to be damaged during the transportation. So we are involving sheaths, more number of sheaths within the underground cable. So there may be chance of damaging, during transportation. By this, potential gradient value will be vary, and considerable losses in the intersheaths due to charging currents. So for these reasons, intersheath grading is rarely used. So this is one kind of making uniformity of stress within the cable, but due to some disadvantages, intersheath grading is rarely used, not frequently used. So rather than this, capacitance grading is well utilized in making the uniformity of stress. So this is regarding about stress in the cables. So as we discussed, why grading is needed. The grading is needed for, so to make the uniformity of stress, dielectric stress within the underground cable. If non-uniformity happens, the breakdown of underground cable, that insulation breakdown may happens. So because of that, grading is needed. So grading, we have capacitance grading and intersheath grading. Capacitance grading means within the conductor we will use different dielectrics of different permittivities, epsilon 1, epsilon 2, epsilon 3, different types of permittivity materials we will use. So these epsilon values will be inversely proportional to the radius of the dielectric material. So in intersheath grading, we will involve number of sheets, more number of sheets within the conductor, within the dielectric material. So by that we will achieve the uniformity of stress within the conductor. So in next class we will come up with new topic in underground cables. Thank you.